Hi there. During this session I'm going to be talking about the photoelectric effect. This is a really important effect because it represents the gateway from standard Newtonian physics into what becomes quantum physics. So it's really the first observations which allowed us to start to think differently. So let me take you through this. The photoelectric effect works like this. If you shine light at certain metals, then it causes the ejection of electrons. That seems fair enough, but when we start looking at some of the finer details here, we make some interesting discoveries. And that is exactly what happened with what is known as Milikan's experiment. What he did was firing incoming photons at a metal surface, causing what became known as photoelectrons. Electrons displaced by photons of light became released. Now what he was able to do was, by adjusting the voltage, he was able to stop the current. Okay, so normally an electron would be emitted, and what could happen is the electron was able to travel from one charged plate to another. Okay, now see here, remember these are electrons, so they would be naturally repelled away from the negative plate. But if they had enough kinetic energy, the kinetic energy would allow them to reach the target anode. Now what he found was that there was a certain voltage which was able to cause the stopping of all photoelectrons traveling to the anode. Now what that meant was that this voltage showed us exactly how much was the maximum kinetic energy of these photoelectrons. Because if they had any extra energy, it would allow them to overcome the voltage and make it to the anode and create a current and a flowing round. But he found that there was a certain voltage, the stopping voltage, and that stopping voltage multiplied by the charge of one electron would tell us what the kinetic energy is, or the maximum kinetic energy of any of these electrons. Now that was kind of interesting and kind of useful. So there seemed to be a certain point when the photoelectrons didn't have any more energy. It was their maximum kinetic energy. So from this, further observations were made. Number one observation was that if you increase the intensity, you can increase the number of photoelectrons. So that means the amount of electrons creating a current could increase, but it didn't increase their kinetic energy. So that means that stopping voltage stayed the same. Interesting observation number one. Observation number two was that the energy of the photoelectrons is actually linearly related to the frequency. So if you increased the frequency of light, it meant that the stopping potential, it meant that they had more kinetic energy, but it also meant there was a threshold frequency, okay, below which no electrons would be released. Okay, so you have to increase the frequency up to a certain point, and only after that point will electrons begin to escape. Now what's surprising about these observations? Okay, first of all, the fact that the intensity of incident light does not affect the energy of the emitted electrons. So that means no matter how bright the light is, the energy isn't impacted. So what controls the energy of these electrons? Then there's the fact that, okay, well actually the energy depends on the frequency of the light, not the brightness or the intensity. So that means the frequency must have some impact on the amount of energy being provided. Then there's a minimum frequency. Okay, so that means that energy must reach a certain amount for electrons to be emitted, and below that frequency nothing happens. And also finally, electrons are emitted instantaneously. This point wasn't really covered clearly in those observations, but what happens here is that when you turn a light on, straight away electrons are emitted. If we had a concept where by giving more light, that means the energy would build up until eventually they were emitted, well, that would cause them out of time. But that doesn't happen. It means that when an electron is emitted, as soon as the light hit it gets emitted. So there must be a relationship there of some sort. Now, Einstein put forward a hypothesis relating to this, and he stated that light must consist of quanta, or packets of energy and momentum. It's not just one continuous flow of light. It means that they come in chunks of some sort. And the energy of one quanta is given as this. Okay, the energy equals a h, which is known as Planck's constant, multiplied by the frequency. So what we're saying here is light comes in packets of distinct energy dependent on their frequency. Now, those quanta of energy, we're going to get the term photons of light. Okay, so each quanta, each chunk of energy provided in this form is known as a photon of light. So now let's look at this idea with the idea of photons of light. Now what we have here is if we have a high energy violet quantum of light coming in. Now what that can do is it can provide enough energy for the electron to escape and some additional energy, which is the kinetic energy of the electron as it leaves. So we have two formulae here. The kinetic energy of the electron when it escapes is equal to the total energy of the quantum of light as it entered, and that's multiplied by Planck's constant multiplied by the frequency, minus what's known as the work function, and that's the amount of energy required for the electron to escape what we consider as an electron well. Now this work function actually is going to relate back to that frequency which is required to reach to escape an electron well in the first place. So let's see this graphically. Okay, so what we're saying here, if the kinetic energy is equal to hf minus this work function. Now what we have here, if we plot the energy of the electron, the kinetic energies of the electron against the frequency. Now first of all, there's a certain threshold frequency before which no electrons escape. So that means that, although we can't plot it here, the kinetic energy, or there's no kinetic energy because there's no electrons escaping. Past this threshold frequency, what happens is, as we increase the frequency, then the kinetic energy increases and the slope of that graph has a gradient of h. The intercept of this straight line, which we plot, we will see will be equal to minus this work function. So that means it's the amount of energy required to escape. And as it happens, that work function is going to be equal to h multiplied by the threshold frequency. So once we do that, that should equal the energy required to escape an electron well. Here's a question. A photo surface has a work function of 1.5 electron volts. Find the critical frequency, that's the threshold frequency, which is going to allow electrons to start to escape. If the light of 6.1 times 10 to the 4 Hertz falls on this surface, what is the energy and the speed of the emitted electrons? So there's two questions here. I'll give you a moment to try and work it out, and I'll show you how you do this. So first of all, the critical frequency. Since the work function is equal to the critical frequency multiplied by Planck's constant, I can then work out the frequency is going to be 3.62 times 10 to the 14 Hertz. Any light which has a frequency below that is not going to escape, cause the photoelectric effect to take place. Now, if I've got a kinetic energy of the electron is given by the Planck constant multiplied by the frequency minus the work function. So that means I can work out that in this case I've got a new wavelength, so that gives me an energy overall of 1.64 times 10 to the minus 19 joules, so that's the kinetic energy, and by rearranging half mv squared I can work out a velocity of these electrons is going to be 6.0 times 10 to the 5 meters per second. So final review. The photoelectric effect told us that light, when it has a frequency which is too low, or wavelength which is too long, remember those two things mean the same thing, then it will cause no electrons to escape. If light has a shorter wavelength and therefore a higher frequency, that means that the electrons will escape, and what happens is the amount of energy, the kinetic energy of these electrons, will increase as we increase the amount of energy being provided in these what are known as photons of energy. And a photon of energy is going to be equal to the Planck's quantum multiplied by the frequency.